Yeah, thanks a lot for this opportunity to present. So, yeah, I'd like to talk about thermal fluid modeling and composing thermal fluid and process models, so process engineering models with scientific machine learning using Julia. So, a little bit about me. I have a PhD from NTNU, and then I worked at Syntef briefly, and then moved last year to become a software engineer at Julia Hub. And so I would be talking about the thermal fluid part, and towards the end, Vinny will talk about the process modeling part. All right. Okay. So yeah, just I should move this. All right. So talking about like the kind of overview of thermal fluid modeling is you have fluids in a pipe commonly. So say you have a flowing fluid, say, and you're adding heat to that fluid. And usually the interesting applications involve some kind of phase change. So this is from, say, liquid to gas, or yeah, that's commonly the most interesting example, as or gas to liquid, like condensation, evaporation as a result of heating. And so this kind of phenomena is inherently challenging. So this sort of two-phase phenomena is inherently challenging, particularly because it involves stiff dynamics. So as an example, if I have this pipe and evaporation, and we look at the densities of the medium as it's heated, there's usually a very sharp change over a very small time scale. And commonly, these fluid models are coupled with other sort of lower time scale cases. So for instance, the temperature of a room, and in that case, the dynamics could vary in like 1 or 2 or even like 3 orders of magnitude. So stiffness is a major issue. So this is particularly important in like building and HVAC models, where the sort of building dynamics move in the order of minutes or hours, and the HVAC, say the pressure models of HVAC change in the order of like 1/10 of a second or lower. So this motivates the a stiff requirement of adaptive solvers for these stiff dynamics. There are a number of other issues with fluid modeling. So for instance, we could have compressible, turbulent, viscous flows with heat transfer. And sometimes you have like discontinuities at these phase change boundaries. All right. So saying a little bit more about this discontinuities, we for instance can, like, if we look at, say, a pressure enthalpy diagram. So this is like a pipe being heated in a refrigeration in a vapor compression cycle. Commonly at the point of evaporation, densities and their derivatives change very quickly. So in addition, it's not getting this media or refrigerant models tends to be like a major challenge here. So I'll talk a little bit about the approaches we have. So for instance, one can use, say, the open source tools like CoolProp or RefProp here. But then generally these sort of equation of state models tend to be fairly slow. So one of the approaches we developed as part of the Julia Sim product is to train fast and accurate B-spline models in order to have and make sure they are consistent with regards to mass and energy conservation. All right. In addition, so again, this is very much so we have so just kind of presenting the overview of the approaches to solving these thermal fluid modeling challenges. So we have a kind of platform product called Julia Sim that is built upon Julia and the SciML toolkit. We have it's designed with modeling toolkit, which is this symbolic modeling language. And then the third layer is we have a bunch of component models that are added, like multi-body, HVAC, fluid models, and battery. And in addition to some workflows, common engineering workflows like calibration control and acceleration with surrogates. So one of the strategies that is employed here, so we use a lot of commonly, so the idea is to translate a lot of the discoveries and techniques that were implemented in the Modelica fluid and media library. So this is so Modelica has this tradition of solving these problems over, I think, 10 or 15 years. So what we've done is got the best of these and then brought them into uh, into into the Julia world. So for instance, and also some sort of CFD related strategies like having like a staggered grid in which you alternate mass and energy balances with momentum balances, having upwind discretization and so on. And the Modelica world introduced some ideas like stream connectors and like model structure in order to handle these difficult thermofluid modeling problems. All right, so I'll give a demo now, but just to provide an overview of so we have three separate products that are kind of related. So one called Julia Sim HVAC, which is targeted at vapor compression cycles. So on the right here, I have an illustration of a vapor compression cycle. So one would have the evaporator, which is the part inside the room in which heat is removed from the room to cool the room. So evaporation, so cooling by evaporation, and then the refrigerant is compressed to a higher pressure, and heat is lost to the environment, and then there's a valve. And so this is the simplest example. One can have like more complicated variants of these. So what the HVAC model provides is a set of pre-built components. So for instance, tube fin models for the heat exchangers, compressor models, valve models, fan models, condition spaces, and so on. So these are so we provide a 1D like a finite volume model of this 1D like with 1D assumptions. All right, we also provide thermodynamic property models. So for instance, spline-based thermodynamic property models for a bunch of refrigerants. This tend to be in the order of 1,000 times faster than, say, using cold prop. And also air models like dry air and moist air. And these are very much media models. So that's in the Julia Sim media. And these are very much inspired by the open source Modelica media library. So we're currently have like work in progress is to try to integrate these with Clayperon for like to have like a larger set of property models. But yeah, that's I think Vinny will chat a little bit more about this. So in addition, there's this like ecosystem to SciML. So as I mentioned, calibration, solvers, optimization, AD, surrogates, and control. So yeah, I'll give a quick demo of this vapor compression cycle in which you have this 4 condenser, evaporator, compressor, valve model. So I'll just switch here. So as I mentioned, we provide pre-built components for these, and so in terms of workflow, one would import the required packages. So for instance, modeling toolkit, which is a symbolic programming language, and solvers and so on. We also import coolprop, but in this case, just for comparison, it's not a dependency. And part of the platform also provides this Plane models for refrigerants and other media. So in this case, if we're to have a refrigerant that is R32, so one would load this refrigerant and then define a bunch of initial conditions that one can set. The evaporator pressures. In this case, we're assuming we set enthalpy. We can set charge and so on, compressor settings and so on, and then certain boundary conditions like the relative humidity and so on, and control inputs as well, which are set over here. So then we provide certain like pre-built components like a compressor model. So in this case, it's a speed-based compressor model, an LEV model, and so we have like a more detailed tutorial in our documentation about the tube fin heat exchanger, but then one can put in things like the length of the pipe diameter, so the usual parameters that one would have, and then the idea is to match Modelica semantics as much as possible. So like the Modelica fluid has this idea of model structure, which is I would not get into, but it's a way of having staggered grid, like of alternating flow cells with energy balance cells. So and then one could set up the number of finite volumes, the number of tubes, number of circuits, and so on. The tube diameter, and then set up the and then call the heat exchanger, the heat exchanger for the condenser, evaporator with air, and so on, and then connect the entire system. So in this case, it's just a single level vapor compression cycle, compressor, condenser, LEV, evaporator, and so on. And then the general idea in modeling toolkit is you would begin by defining the ODE system. That is a collection of all these components connected together. So yeah, in this example, we see that we go from, I think the full system had like 1,172 variables, and then that is reduced to like 71 independent variables or 71 state variables. And so the simulation is done on this lower system of 71 state variables, which and 71 equations, which form a differential algebraic equation system. So as I mentioned, there are a number of solvers that one can use. So we also have a more robust initialization system. So consistent initialization of the DAE tends to be an interesting challenge. So we have some more tailored algorithms for solving that nonlinear optimization problem, or that nonlinear equation system. And in particular, when you use a large number of nodes or large number of finite volumes, this tends to be a large system. So that's scaling to large systems tends to be important. And so there's some decomposition strategies, or like there's some strategies to solving this initialization system that we implemented. So then this ODE problem can be solved, and we have the Julia ecosystem to plot the results and so on. So for instance, one can see the quality of the evaporator in the different control volumes. So, for instance, in the like we see in the quality of the refrigerant in the evaporator in the different control volumes. So we see the, for instance, as expected, you kind of have an increase in the quality during evaporation, and a decrease in density. And you can query all these parameters. And we see during condensation, you have a decrease in the quality of from fluid to liquid. Sorry, from gas to liquid. So yeah, so you can plot all these things. So just so moving on to the so yeah, there's some details on how to set things like geometry models, flow models, pressure drop, friction calculations, heat transfer models, and so on, which I'll skip over. But then discussing a little bit about the ecosystem. So just getting back to this. Oops, sorry. So the idea is you can compose any Julia packages. So you can compose HVAC and battery. So we have some examples of battery thermal modeling. Or so, for instance, for an electric car, the battery is cooled and with a chiller that um, is integrated with the HVAC system. So you can combine these two models seamlessly out of the box. And you can also combine with these other workflows like universal differential equations for model discovery, calibration control, and surrogатization. So I'll just quickly talk about the calibration example and also talk about the Julia Sim fluid. So the fluid and media libraries are more general than HVAC. So for instance, if you have like, so Julia Sim Media, which is meant to be as an analog to the Modelica media library, we can have, say, glycol as, which is commonly used in a battery chiller. So in this case, as a simple example, one would the media library provides the properties of glycol, and in this case, I'm just putting together a heat exchanger model of just two glycol pipes with each other. I'll leave this in the details here in the documentation just to show that in terms of calibration here, you can do model calibration to data. So assume you have some data and you want to assume you have some data and you want to calibrate a model to that data. So this can be done in 6 lines of code with one of the tools called Model Optimizer that performs this, say, least squares optimization problem. So we just define what's called an experiment, and one can choose between like single shooting, multiple shooting, collocation, and so on. And there's a single API call to calibrate to data. So for instance, just to present the final results, so if one has data experimentally in this sort of 6 lines of code, one can put in the data, calibrate the parameters of the modeling toolkit model to data. And this relies heavily on automatic differentiation, forward diff, and so on. So solving the optimization problem with derivative solvers. Sorry, I don't have time to go through all this, but it's just there's a bunch of documentation here. The other idea is to perform acceleration with surrogates. So we have this digital echo, and so again, one can pass in an FMU or a modeling toolkit model, and from this date, once enough data is generated, we are able to perform acceleration. And for instance, in this case, we tend to get pretty, in most cases, get line over line models compared to the ground truth, with usually 1 to 2 orders of magnitude speed up, especially over FMUs. And also, this tool seamlessly composes with the control tools, which have been presented, I think, at the last Digiwell quite substantially. So, for instance, with MPC, you could compose the HVAC or battery tool with MPC quite quickly. So yeah, I'll stop there and hand over to Vinny to talk about the process modeling.
Okay, so I'll try to be brief to not go over the time of other presenters. But first of all, thank you for an invitation to be here. As we have talked through this very brief presentation, will be more about sharing an idea than an actual implementation of the idea. Well, the title is Process Models with SciML in Julia, Motivation, Challenges, and Opportunities. My name is Vinicius Vieira Santana. I'm a postdoctoral researcher at NTNU, the Department of Chemical Engineering and PSE group here in Norway. And also, this work also counts with the participation of Avinash from Julia Hub as well. So, let's just, I will just start with the definition of what I mean with process simulation. When I say process simulation, mechanical process simulation, which means a model-based representation of chemical unit operations like reactors, distillation columns, heat exchangers, and so on. These are good examples of what I mean by chemical unit operations. And these unit operations are connected by material streams, and these unit operations perform thermophysical or chemical transformation on these streams. For instance, they can be used to change temperature and pressure, purify the inlet streams, or convert reactants into products, for instance. So, because process simulation can mean different things for different people from different backgrounds. So I'm just trying to make sure that I'm doing the correct definition here. So the history behind process simulation is quite long. And in order to know how to go in the future, we have to know what happened in the past, right? So it's well known that commercial solutions are available for a while, and everything started about the mid-50s with the world's first steady-state simulator. And in the late 70s, the Aspen project was founded at MIT, not the Aspen company, the project. And then meanwhile, other softwares appeared like GPROMs, which is very famous for dynamic simulation process. And then by the late 90s, these software companies carrying out process simulation, they start to realize the need of dynamic simulation in these softwares, because mostly chemical companies start having more specialties in their product portfolio. And these specialties very often require batch processes, which are modeled through dynamic equations. So the need of this made companies aware that they need to include dynamic simulations into their portfolio of products. In terms of open source software, process simulation can be mapped, I would say, to 2008. Of course, I haven't included all the players here, but I have included probably the most popular ones. The first one I know is the DWC, which was made for steady-state simulation by Daniel Wagner, which is a Brazilian guy. As far as I know, he's the only developer of this library, and the name of the library comes from his name, Daniel Wagner. And then in 2016, the IDAS project started to gain traction, and they are heavily based on the PyAML algebraic modeling environment. In the web page, they claim that the dynamics is supported, but I haven't found any example of dynamic simulations within the ecosystem, but they have support for it through the PyAML DAE library. They also support surrogate modeling and uncertainty quantification. Then in 2019, the Modelica, there has been an effort to make chemical process simulation in Modelica to what they call the OEM ChemSim library, which is an open source project now hosted in GitHub, and people can just check and use. So as part of Modelica, it supports dynamic simulation, but as the authors claim, they had minimal support for thermodynamic calculations. Also, the last commit of the package was about 4 years ago. I don't know the reason they stopped maintaining it, but the fact is the last commit of the package was 4 years ago. And then I can't forget to mention this ENSO library. It's an environment for modeling, simulation, optimization, which dates back to 2003. It was developed by some researchers in Brazil, and it supported dynamic simulation. It had a symbolic differentiation system, robust DAE solvers with good initialization algorithms as well. They have a GUI interface. It was very ahead of this time for 2003, and it was free at the time, but it was left in disuse. I don't know the reason why. So with that background, we can ask ourselves, so what will come next? And what's needed to succeed with what will come next? So regarding what will come next, I believe that Julia and the SciML ecosystem can be the platform for the next open source solution for process simulators. And to map the success factors to do this, I brought one example. It's not open source, but it came from a company, DuPont, which is one of the greatest chemical companies in the world. So they developed their own process dynamic simulator, which is not open source and it's not commercial. It's for their own use. They call these T modes, and dates back to 1992. And the motivation behind it was that they wanted all the engineers of the company to make dynamic simulations part of their daily activity as engineers. However, they were not satisfied with any commercial solution, and they decided to do their own. And despite this tiny development team and flaws, the T-modes became a tool that all processing control engineers used in the past and still use for their projects. So some engineers from the company wrote a paper about this software and highlighting the points that they believe that made the T-mode so successful and useful within the context of chemical process simulation. So what factors are these? And how can we learn from these factors in order to try to do the next open source simulator of chemical process? So I brought some of the success factors they listed and how the successful factors could be incorporated or already available in Julia. So one key factor is the access to thermodynamic models and data. So in this sense, Julia has Claypron.jl library, which is a Julia native open source library of thermodynamic models with more models than any package available so far and with great performance. They also mentioned you should have a library of unit operations and no solver worries, meaning that these unit operation objects, they have to be robust, easily configured, which means good defaults and flexible. And also the casual modeler using these models needs to be able to focus on the process and not on the solving things behind the simulator. And in this sense, the fact that Julia has declarative symbolic model language like modeling toolkit allow the developers to focus on writing modular compact high-level representation of the process of the unit operations and let the compiler do the work of simplifying the models. And the third factor brought is the speed. So they claim in this paper, the Gox and Smith that and Dimitratos that the model have to run fast, ideally 50 times more than real time. Of course, that for some systems that's impossible. But the fact is, Julia has a comprehensive ecosystem for dynamic simulation, very high performance numerical solvers, like in nonlinear solver.jl and differential equations.jl library. Well, with that in mind, we are proposing the process simulator.jl library. So that's an initiative with the collaboration between 10U, being led by me and Professor Defonso from the IKP department as well, and the PSE group. And also Julia Lab and Hub with Chris and Avinash as well. And then we are counting with the support of Claypron's.jl library developed by Andres Hiedemann. Of course, more people are welcome to this. One of the reasons we are talking about this is also to try to, spark the interest of people to collaborate as well. So as unique features of the library, we can list the goals we have for the libraries is to make into open source, of course, and part of the SciML ecosystem. Because as I have shown from the history, there's a lack of open source software that effectively supports dynamic simulations of chemical process, particularly for batch systems where specialty chemicals needed to execute simulations. And also the fact that we have this whole ecosystem of SciML with, for instance, hybrid models. That's very interesting for these kind of simulations on specialties because they have very complicated systems like crystallization, some complicated reaction engineering, that the hybrid models available in the SciML ecosystem can be very, very helpful. So of course, we also need an open and extensible thermodynamic models through a library, and Claypron seems to be the most interesting solution this way. The fact is fluid properties are the base for any first principle process simulators, and we believe that Clapeyron.gl do this job very well. And also symbolic transformations and automatic differentiation. So we can leverage the capabilities of modeling toolkit with declarative symbolic modeling and the existing automatic differentiation packages available in Julia, like 4diff, Zygote, Enzyme, and ReverseDiff, for instance. So with this, we aim to achieve robust, fast, and accurate process simulation.